Hello, welcome to Zig for the Uninitiated. My name is Tyler. Let's get started. Today, I want to talk about floating point numbers and the floating point format. And this is actually a topic I've wanted to talk about for a while, but haven't done it in Zig for the Uninitiated because I haven't really found a Zig specific reason why. Floating point format numbers, they exist in pretty much every programming language. And so it's not something that's specific to Zig. But I think understanding the format is something that is important as you start to learn how to program at a more lower level. And lo and behold, we get the 0.16.0 release. And in it, there's a little tidbit that I think provides a perfect example of where it can be useful to understand floating point numbers. So if you don't know, 0.16.0 was released just this week. And it's packed full of a lot of new changes for Zig. One of the big ones is the I/O as an interface. That's something that we're going to get into in another video at some point once I play around with it and learn about it. But apart from that, there is a tiny bit here in the language changes, right? Where is it? Oh, there. Allow small integer types to coerce to floats. So I'm just going to read what it says. If all possible values of an integer type can fit in a floating point type without rounding, the integer may coerce to the float without an explicit conversion. This is determined by comparing the number of bits of precision in the integer type and the significant in the floating point type. Larger integer types will still require float permit. And it has this example of in the past, say you had this U24, so a 24-bit integer, 1, 2, 3, and you wanted to convert it into a float, you'd have to use float permit. Now, if you had that same integer, but it was a 25-bit integer, you'd also still have to use float permit. But now on the new version, 0.16.0, you don't have to. For the first example, we do not have to use float permit. This conversion is guaranteed to be safe. And this is not really a new feature of the language. I mean, it's a new feature of the language, but it's guaranteed to be safe, not because the language does anything, but because the format, the specification of what a 32-bit floating point number is, means that this number is guaranteed to be representable in the floating point format. So that's what I want to explain. I want to explain why we know that the U24 can be represented, but not the U25. And to do that, you got to understand what floating point is. So I'm going to start with a few examples here. We're going to start actually with integers, or not integers, with decimal numbers. So a lot of programmers, you know that when we talk about floats, we're talking about numbers that have probably fractional parts or have decimal points. That's a lot of times that we think about that, or a lot of maybe as a shorthand. You might say, oh, a floating point number is a decimal number, which isn't precise, ironically, because they're not exactly decimal numbers. They're used to represent numbers that can have fractional parts, but they're also used to represent integers that are very large or really small numbers close to zero. They don't have to have necessarily a fractional point part. They can be very, very big integers. But a lot of times we think about them in the fractional point part. So if we had a number, say, let's say we had a decimal number, right? Let's do 123.45, right? 123.45. We could write that, right? If you went to, high school, you probably learned about scientific notation and say, oh, that another way to write this number would be 1.2345 times 10 to the, and we'd say, oh, we went 1, 2, we went 2 decimal places over, so we times 10 to the 2. And so, yes, because if we took this number and multiplied it by 100, look, we'd get that number, right? 10 to the 2 is 100. 1.2345 times 10 to the 2 would be the exact same number as this. We call this scientific notation. And if you understand scientific notation, you understand the keys to understanding floating point format. Because when we say floating point, we're actually talking about this decimal point in base 10. We are allowed to float that point around in different places just by shifting the number of times we multiply by 10, right? So if we wanted to move it over here, we just subtract 1 from there, right? But we don't want to do that. So let me just undo all that. What I want to talk about is the different parts of this scientific notation. We can say that in the scientific notation, we have two parts. We have this part, which we can call the fractional part. It's also sometimes called the mantissa or the significand, which is what the Zig docs just used. We also have this part right here, which is the exponent, right? We don't really care about the base of the exponent because we know we're dealing with decimal numbers and we're just shifting the decimal over, that we're always multiplying by some power of 10. So what we really care is what that power of 10 here. Here we're raising it to the second power. And that is, in essence, the key parts of what is encoded in a floating point format. To give an example of what we do in floating point or with binary numbers, you can think of a binary number with a fractional part. We could say it's 1, 0, 0, 1, 0.1001, right? This would be, let's see, 1001, that is 9, and then point, and you have a half, and let's see, not a quarter, not an eighth, but a 16th. So 1/2 plus 1/16, that would be, what is it? 9/16? Yeah, 9 and 9/16. But we could represent that in a scientific notation standard like this: 1.001, make that 0 look better, 1.0011001. Okay. And then we're going to multiply it by some exponent. And what are we going to do? We're going to multiply it by 2 to the, how many times did we shift this over? 1, 2, 3. 2 to the third. Okay. Add a little multiply here. Okay. And that is our scientific notation version of this 9 and 9/16. It can be represented as 1.00111 times 2 to the third. So if we have this, the question is, how is this actually represented in the binary format? And let's talk about that. In binary format, we're going to use the 32-bit floating point format here just because it's smaller, easier to draw. The way we could represent this is first and foremost, I'm going to write this. Make sure we know that over here is the most significant bit to least significant bit, okay? Meaning the bit over here represents the largest number, and the bit over here represents 1, essentially. So from most significant bit to least significant bit, we start out with first 1 bit. That 1 bit represents the sign. So we'll write, we have 1 bit there. Then we have 8 bits right here. These 8 bits are used to encode the exponent. And finally, we have 23 bits here, the rest of the 32-bit number. We can check 23 plus 1 is 24 plus 8 is 32. So yes, the rest of the 32-bit number represents the fraction. So how would we encode our example floating point number here in the floating point format? Well, here's what we do. First, let's set the sign bit. That's the easiest. The sign bit is 0 if the sign of the floating point number is positive. Well, we have a positive number, so we're going to put 0 here. We're going to skip the exponent for a second and just go into the fraction. In the fraction, all we have to do is encode the fraction. We want to take the 23 bits that we have and write down this fraction. However, there's a little trick that we know here, which is that when we use scientific notation, we always can make this leading bit a 1. And so if we're going to use that leading bit a1, we can just imply that that leading bit exists here. That actually gets us a extra bit of precision. So we actually have 24 bits of a fractional part because we always assume that that first one is a 1. Okay, there are cases where that isn't possible, but that's more of a special case. We're going to talk just about normalized floating point numbers for right now. So we take that 1, right? Assuming that that 1's here, then we're going to write down the rest of the bits of the floating point number in. So we have 0, 0, 1, 1, 0, 0, 1. And you can see, right? This corresponds exactly to the parts of the floating point number with this leading one implied. So that just leaves, and then the rest are going to be 0 because there's nothing else. So the rest of the 30, rest of the numbers will be 0. Rest of the bits will be 0, I should say. And for the exponent, we know that 2 to the third, right? We really care about this number. We don't care about 2 or 2 to the third. We just want to encode 3. That we're going to raise this value to the power of 3, or really shift it over 3 times. What does that mean? Well, sorry. So since we only care about the 3, we could think of just encoding 3, 1, 1, and then have 0, 0, 0, 0, 0. See, 1, 2, 3, 4, 5, 6, 7, 8, right? And say, hey, there's 3. But that runs into a problem. What if we wanted to encode a negative number, right? Or a negative exponent? Well, if we had a really small number, we'd want to be able to encode this negative number. And so what we do, or what the specification says, is that we start in the middle. We start at 127. And 127, right, an exponent value of 127, i.e. 1000, right? Basically, this one is leading 1, is 0. And then we can count up from there, or we can count down from there. So 0 is negative 126. Anyways. So this is how the number would be encoded. 0, 1, 0, 0, 0, 1, or sorry, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, and everything else is zeros after that, right? And that is how you could take some binary number that you can write and encode it into a floating point, F64 or F32, a floating point, a 32-bit floating point number. Now, the question might still remain is, but okay, how can I still encode? How do I know that, my U24 can encode into a floating point, a 32-bit floating point number? And let's just take this as an example. Say you had this integer, 1, 0, 0, 1, 1, 0, 0, 1. If this was your floating point number, you notice that you could encode this as, or in scientific notation, this would be 1.0011000 times 2 to the, and how many times do we move it over? 1, 2, 3, 4, 5, 6, 7. 2 to the 7th. Okay. And what you'll notice is, other than the exponent, this would be encoded the exact same as what we just, this number, right? These numbers are the same, other than that we're shifting this exponent around, which is right here. The exponent only changes the value here, which case this number is going to be exactly the same. And we realize that this number, this part of the floating point number is an exact copy of every bit in the integer minus that leading one. And so we can learn that, okay, then any 24-bit number is encodable inside of this floating point number, because we have 23 bits to work with, 23 bits here, plus that leading one with the 24th bit. And that is how, as we see in the release notes, we're able to prove, or able to guarantee that this U24 is encodable in a floating point F32 value. Now, to illustrate this a little more, I wrote a simple little program here in Zig that illustrates it. Let me zoom in here. There. Okay. Just kind of perfect. Okay. Okay. So I wrote this little program here, and all it does is it takes in some integer. It'll parse the integer. It will convert that integer into a float, meaning it'll take that integer and convert it into floating point format, kind of what we just showed on the Excalidraw. And then it takes that float and converts it back into a U64, but it bit casts it, meaning that we just take the raw bits and treat it as an unsigned 64-bit number. So that way we can actually play around and look at the bits of the number. So if we take float and we say, let's pass in 100, we can see here we have this binary representation of 100. We have the floating bit representation of 100. And in the, this is a 64-bit floating point representation. You can see that the leading number, 0, is a sign. We have these next 11 bits that are dedicated to the exponent. And then we have the rest, which is the fraction. And if you look at the fractional part, you can see that it is an exact copy of all of the integer bits minus that leading one. So then we can start throwing in really big numbers, 1, 2, 3, 4, 5, 6, 5, 6, 7, 8, 9. And you can see that this counts. In fact, this will work for any number up to 2 to the 24th. Or no, 2 to the 24th plus 1. So 2 to the 24th is 0x 1 ff, or 0. Essentially, the maximum 24-bit floating point number is going to be 1 ff 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 ff. Let's see, how many is that? 1, 2, 3, 4, 5, 6. Oh, I missed one. There we go. And you can see that this is the maximum integer that we have, and it is represented right here. Exactly. Now, it's not the largest integer that's exactly representable. In fact, if we just did this, added one more to it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, off by 1. There we go. You would see that we are losing this 0 bit of precision, but it doesn't matter because it's a 0. That 0 doesn't matter. We kind of just assume that everything after this is zeros. So we can represent this number, but we're not guaranteed to represent every number in this 25-bit space. In fact, if we add just one more, we can see that we get the exact same floating point number. This floating point number exactly matches this one. And so there's some rounding error here. And then we're at this point where odd numbers are not exactly representable. They are going to be rounded off, whereas the even numbers are exactly representable. And as you go further on the floating point, past this point, there are larger and larger gaps between representable integers. That being said, 2 to the 53rd is very large because, once again, this is 64-bit floating point format. You have 53 bits and the significand to use. That's it for this video. I hope it was enlightening about some floating point stuff. There's more to understand about floating point, particularly how denormalized values work, so values where you can't have that leading one, so numbers that are very close to zero, essentially, and how you deal with numbers that are not actually numbers. Nans and also infinity are encodable in the floating point format. Maybe that's a video for another time, but I really wanted to show this and illustrate how that knowledge can help you understand things like this particular small note in the release notes in Zig. Have a good one. I'll see you later.